Hello, everybody. Welcome to this session. My name is Kapil Aurora. I am a cloud solution architect at Netapp. For those of you who do not know about Netapp, Netapp is a data management company. We have solutions from all-flash storage to software-defined storage and a lot of solutions in Amazon Web Services as well. I personally work on all the open source technologies that Netapp integrates with, and Kubernetes is one of them. And that's why I'm here to talk about persistent data. So Netapp deals with data and works on data. So that's why that's the topic that is very, very important to Netapp as a company, and me working with Netapp and at Netapp for our customers, right? So most people who are working with Kubernetes are definitely deploying applications which are stateless, but not everybody is deploying applications such as databases which have a state or which have the function of actually storing the state of the application, right? So we do not have a lot of time. I just have 30 minutes and it's a very broad topic. There are lots of concepts to understand. So I have tried to keep it short and made it a very demo-focused session. So I have a demo, but before that demo, I will try to explain a few concepts so that we are able to follow the demo when we actually do it. Yeah. So we will spend most of our time on the black screen or blue screen that I have. And I will, before I start the demo, I will try to go through some concepts so that if you're not aware of these concepts already, you can follow the demo, right, and understand the concepts. All right. So the first and most important concept is persistent volume, right? And it is important to understand that Kubernetes itself understands different kinds of persistent volumes and is able to mount them and offer those storage to your pods or to your containers, right? So if you see on the left hand side here, you can see different kinds of storage like NFS or Amazon's what does Amazon have? Sorry? EBS, exactly. EBS or Azure Disk or GCE PDs, they are called. All these storage types, they are well understood by Kubernetes itself. So if you look at the diagram on the right hand side, you will see that that is actually a representation of Kubernetes node, which has a process called kubelet running on it. And this kubelet process has drivers which understand how to mount or attach these particular volumes, and it understands all these volumes. So as a consumer of Kubernetes, I can use all these different types of storage devices and store my data on them. But when I'm working as a developer on these platforms, I probably do not want to deal with all these storage types. I do not want to understand what iSCSI is. I don't really care. I just want to store data, right? I do not want to care if the data is stored on NFS or iSCSI, it's a LUN or whatever it is, right? So that's very, very important as a user, right? As a developer, I totally do not want anything to do with it. So if I tell a developer this is the iSCSI disk and go and mount it, that's too much work for him, and he's probably not the expert to do that. So that's where I want to introduce new concepts in Kubernetes, which are based on persistent volume claims, right? So the developer has nothing to do with persistent volumes anymore. He deals with claims. He says what he needs. He says what he wants. And there I will try to explain to you what is static and dynamic provisioning in the next two slides that I have. All right. So what does a cycle, or how does a developer interact in the system, right? That's what we are trying to look at here. So if you see here, I have a developer. I have some storage systems or any kind of storage on the right hand side, which only the storage administrator, the cluster administrator has access to, right? The developer cannot actually go to the storage system and create or provision volumes. So we are talking here more or less on the side of things where developers do not have direct access to storage systems. That would how it would happen in enterprise environments, for example, right? Even if you have Amazon accounts, you will not just let developer provision whatever he wants to provision, right? So you'll have some kind of control at some level. So in this static provisioning, what happens is an administrator has to pre-provision certain volumes. He has to provide the system or the Kubernetes environment with different kinds of volumes. So here you can see that the cluster administrator actually provisioned two PVs, persistent volumes, which are of different types like NFS or iSCSI using different storage systems. And then the developer comes in and says, I want to run 2 applications, and these applications need so much storage. So one application needs 5 gig, the other application needs 8 gigs. So because there was already available storage in the environment, right, which the cluster administrator had prepared, Kubernetes controller, PV controller, there's a process which runs in the master nodes, is able to map these requirements of the developer to the existing volumes, right? And here you can see that the developer asked for 8 gigs, but the available one was 10 gigs. So that was the best possible match, and that is what is done and created. So this is how static provisioning in Kubernetes works, or how PVCs, persistent volume claims, are created by the developers, and persistent volumes are created by cluster administrators, or somebody who has rights and access to creating volumes. All right, so now the second concept I want to introduce to you is dynamic provisioning. What if I want the storage volumes to be created on self-service? I do not want somebody to actually create them beforehand, to pre-provision volumes, right? So let's see how that will work. So again, I have the same environment, right? But in this case, I need something called a provisioner. I need something which can actually talk to the storage system, or talk to the storage provisioning, talk to the cloud environment, and actually create these volumes for me. In this case, I have a storage system which can define different kinds of storage based on IOPS levels, right? So what happens in this case is I define different storage classes. So this is the new concept. So far we have understood persistent volume claims, persistent volumes, and now we have a new concept called storage class, right? A storage class is something that a developer can use to actually say which kind of storage he needs. So now in this case, when the developer says I need so much storage, the provisioner comes into play and actually creates that on demand at that particular moment when the storage is required. So there's no pre-provisioning required in this case, and the cluster administrator only deploys the provisioner and sets up the environment in such a way that dynamic provisioning or self-service of storage can happen within the Kubernetes environment itself. So this is very, very important. If, for example, I want to run a MongoDB application, or I want to run a Postgres database in Kubernetes environment, and every time I need to create this database, I need to ask somebody to actually create volumes for me, or I need to make sure that there is a volume available for me to use, right? So this is very, very important to create on the go, or as a developer to create different applications which are actually stateful. So this plays a very, very important role and empowers the consumers of Kubernetes. So again, in this case, the provisioner has done its job for provisioning the storage volume, and then the mounting happens by Kubernetes itself, right? Any questions so far? Is it too many new concepts, or are you guys already aware of it? Clear? Yeah? All right. So these were the concepts that I wanted to take you through before I went for a demo. So we are going to use dynamic provisioning, and we are going to run PostgreSQL database. And I've added more things to it, such as Helm charts, so that we can actually do it in a more standardized way. So let me show you what we are trying to do today. So I have a Kubernetes environment, and I want to deploy a Postgres database, and I want to use a Helm chart to do that. So in my Kubernetes environment, I already have Helm installed. I'm able to deploy Helm chart. For anybody who doesn't know what Helm charts is, so Helm chart is a way to, it's a package manager basically. So you can define a template of how an application should be deployed. And once you do that, everybody can actually just say, I want to install Postgres, and they do not need to figure out what is the persistent volume, what is a pod, and they just need to define the Postgres related things. So it's like a catalog creator in Kubernetes, or an open source catalog creator, or a package manager. Okay, so I will show you the one I have created for Postgres, and probably it will be more. And then I have a dynamic provisioner, which is actually going to create these volumes for us. And at the end, we will have a Postgres, which is 2 or 3 replicas, right? A master node and replicas, and they will be accessible through a service. So those will also be created. And we will have 3 separate persistent volumes on a storage system, on which our data for Postgres database is stored. Okay, so that's what we are going to do. And I actually added why we are using Helm, right? So Helm is the package manager, and it can actually standardize the way you deploy databases or whatever you're doing in your environment. And you can follow best practices in your environment. And you definitely need a package manager. You do not want everybody to define their own application. You want to standardize everything in your environment, right? So that is something you definitely need in your environment when you are running Kubernetes or anything in general. All right. So another thing that I'm using here is, so I work at Netapp, so I have lots of storage systems to my exposure. So I'm using a Netapp Provisioner, and it is called Trident. And so Netapp has different storage systems. It works with all of them. The cool thing about Trident is that it also offers things like cloning. So I can clone volumes within Kubernetes, which you cannot do at the moment with the current Kubernetes implementation, right? I can create snapshots of my volumes. And it is an open source project, and this is what I'm going to use. There are lots of other provisioners that are also available. Like if you're using any of these type of storage, there are default implementations. I tried to get it working with OpenStack for meetups like these so that I do not have to use storage systems in-house, but I could not get it working really. It's a lot of work for me. It was a lot of work for me, so I just started using the Netapp Provisioner, and it's easier for me. That's the only reason. But lots of people, for example, who work in Amazon Web Services or who work with Google, they actually use the dynamic provisioning in Google, for example. Yeah, you can set it up like that and use these provisioners. So lastly, I'm using another concept. This is the last concept, I promise. So it's called StatefulSets. So when you're deploying regular applications in Kubernetes, not scale out databases, you do not need a stateful set. But for example, what we are doing is a Postgres database, right? So when I'm deploying a Postgres database and I'm saying create 3 replicas or create 4 replicas or scale this database, I want a new storage volume for me to be created every time, right? I do not. So if you are scaling a regular pod, it will not create a new volume for you, right? So in this case, I need a new volume. And when I'm saying create a stateful set for 3 replicas, what happens is it creates one Postgres instance, then the second one comes up, then the third one comes up. So it creates it in an ordered manner, right? So for any application which is stateful and which can scale out, you cannot really manage it easily with regular deployments in Kubernetes. You need to have stateful sets for it. For example, for MongoDB or anything that scales out and needs new provisioning of volumes. Okay, so these are the reasons that we are using stateful set. Okay, so now I will try to show you in a graphical manner what we are going to do in the demo, and then we are actually going to do that in the CLI. Okay. All right, so this is my environment. I have my Netapp storage system here and a Kubernetes environment on top of a bunch of VMs. And I have deployed the dynamic provisioner for Netapp called Trident. And now I'm going to say Helm install a 3 replica set Postgres database, for example. Okay. So what is going to happen as soon as I do that? Because it's a template, it knows what all it needs to provision in the Kubernetes environment. Okay. So what it is going to do is it is going to create different components. So I've simplified it. There are more components here, but the most important ones. So it is going to create a stateful set. It is going to create PVCs for 3 replicas. So PVC is persistent volume claim. So it's saying that I need so much storage volumes of this much size, and it is going to create a service. So with this service, you can actually access the Postgres database. So these are all objects within Kubernetes, right? So stateful set is an object, service is an object, and a PVC is an object. You can also call them APIs. You can create them, delete them, right? Like you create a pod, you create a stateful set, you create a service, you create PVCs, and the likes. And as soon as there are PVCs in the environment, right, there is no persistent volume right now, right? There's only a claim. As soon as there is a PVC in the environment, the provisioner will come in, right? It will actually do the self-service provisioning of the volumes on the storage system, right? They are created on the storage system. And equivalent objects which actually contain the storage connection information, which are called persistent volumes, are created in the Kubernetes environment, right? So as soon as this is completed, they're actually mapped with each other, right? And then you can see in an ordered manner, each Postgres instance will come up. So first Postgres instance will come up, then the second one will come up, and then the third one will come up. So one master and two replicas, one after the other. And that completes the whole deployment. But the good part is that as a consumer, as a user of this environment, right, I introduced you to a lot of complexity. But as a consumer, I just need to say deploy or install Postgres database, which is 3 replica set. That's it. But internally, lots of different components will be deployed. Storage will be provisioned. A service will be created. A stateful set will be deployed for you, right? So that's the magic of a package manager, right? All right. So are you guys comfortable with this? Can we go and look at the CLI? Yeah. All right. So let's clear this. So I'm right now connected with my Kubernetes cluster. So you can see I have 4 nodes. One of them is a master. We can also see the version of Kubernetes and the client. Then what else can I show? We can also see that what is running right now. So if we say get all, so right now I just have some sample hello pod running, and there's nothing much running in my environment. What else can I show you? So Helm. So I have Helm installed. So we can also look at that. So I have Helm running, and I also have Trident running. Trident CTL version -n. So I have these things are running initially in my environment. There's nothing else running right now. Okay, so one more thing. So if you go to Helm, for example, you can say Helm search, and you will see lots of different stable Helm charts available for you today. So if you want to deploy MySQL or MongoDB, but the one that I'm showing you today is actually non-existent right now in the stable Helm chart. So I had to create it myself. So I have put it on GitHub here. So I have put this in the presentation as well. So I created a Helm chart myself, a template to deploy Postgres in a replica set. So right now there's a Postgres available, which is only one instance. So I had to create this myself. I used the MongoDB one and tried to figure out everything. And I used the Crunchy Postgres container. So Crunchy is a distributor of Postgres, and I used their container installation. So I got this particular Helm chart, so to say, this template on my desktop. So Kubernetes Netapp, Postgres. So this is my Helm chart. So if we maybe look at this, maybe I can make it bigger. So when you're defining a Helm chart or creating it yourself, probably you will have to do, if you are actually using and consuming Kubernetes and you're offering different services in your environment, you will have to write your Helm charts and offer it to your users, right? So I will just show you how it looks like. So you can see this is the folder. In this we have templates. Basically we are defining everything that we need, right? So if you see, I have services, StatefulSets. So I've defined everything in a template format, right? So that they can be, inputs can be filled into that, right? So that's what I'm going to use here. So whenever you have a stateful set, you can use this command called helm inspect, and you can say the name of the name of the Helm chart, right? And then it will show you what this thing actually can do for you. So this is the description that I have provided, that this is a sample Helm chart to deploy Postgres replica set. And then starting from here, it's a configuration. So basically, when you are deploying Postgres database, what do you want to define? You want to define how many replicas you want, what size of the Postgres database you want, what version of Postgres database you want, right? the things that are related to Postgres database, right? For that, I have created a configuration, which port to expose, for example, the things that the user actually knows when he's deploying Postgres, right? The ports, the passwords, the usernames, whatever is configurable when you are deploying a database, right? So all these things can be configured, and for that I have created a config file as well. Oops, sorry. So we can make changes here. We can create a config file and make changes whatever we want to do, right? So I can say 3 replicas, for example, which port, I can change the ports, I can change the name of the user. For example, I've put Kapil here. I can change the images I want to use. I can also restrict, for example, how much CPU, how much memory this particular containers should use, right? So I have all the customizations possible. And from the storage point of view, I'm just saying which storage class I want and what is the size of my volumes, right? That's all. So as a consumer, I just need to provide details that are important for the deployment, and I do not know what a stateful set is. I do not know what is a persistent volume claim. I do not need to worry about all those things, right? So let's deploy it. It's very simple. I just say Helm install. I give it a name, say my PSQL, and then I just give this config file. So far, whatever jargon I've been doing, that is just to make you understand, but the actual installation is just this one single command. There's nothing else. I'm just saying helm install SQL, and I'm providing this configuration file. So I didn't give the chart name. So this is my chart, and now it is actually going to deploy everything for me. I do not have to do anything. So let's see what it did. So it says I deployed this. This is the name. It has been deployed, right? It created a secret for me to store all the passwords. So you can see there are more components than I showed you from the diagram, right? So I also created a cluster role and things like that, which is too much for you to know right now. But just to give you an idea that there are more things that the template is creating, which I do not need to worry about. So we created service. So I created 3 services so that you can directly reach the replica if you want. You can directly reach the master, or you can just say, I just want to read the data. I do not care which particular one is used. I created a stateful set. So it's 2 replicas. So there are 2. And a pod is already started to run. And then there are some nodes. So as the deployer, as the creator of this particular Hemchart, I'm also telling the user how he can get his password if he chose to generate one, and then how to connect to your Postgres database. Right. So let's see what is happening in Kubernetes. So kubectl get all. So you can see a stateful set is created for me, and it's already 2 count. You can see that 2 pods are running. So 2 instances of Postgres are already running. They're in running state, and all these services are also created for me. And let's also look and see if the volumes were created for me. So you can see 2 claims were created for me automatically, right? Because there are 2 replica sets, so 2 claims for volumes were created, and 2 volumes were also created for me. So you can see 2 Postgres volumes are automatically created for the user. So everything is happening in the background. Everything is happening dynamically for the user. So let's also try to connect to the database. So I didn't set a password, so there's a generated one, and this is how I retrieve it. That's my password. And this is the command. So basically I do not need to really worry about anything, and I can just, let's see if it works. So I'm connected to the database, and it's already running. Right. So as a user, it's very simple and easy for me, and everything is actually defined for me within this Helm chart itself. So let's get out of this database. All right. So now the next question is, or next thing that we can do with this database is, now I'm running in a production environment, and we are getting lots of read requests, or the application needs to scale, right? How do I really scale this database? How easy it is, that's what I want to show you. So So I have kubectl get stateful set. So this is the stateful set that has been created, and I'm going to actually make it from 2 to 4 in just one single command. Right. So kubectl scale, I think, minus replicas equal to 4, stateful set, and the name of it. That's it. So to scale this application, which will also involve creation of 2 new volumes, right? I can just do that with one single command. So it says scale, and now if we say, so you can see it is already running 3. So if we say get cores, so you can see the third one already, it's already running 4, right? And if we see the volumes, now we have 4 volumes, and they were also dynamically created from it, right? So how easy it is to deploy a database, right, with a standardized manner with all the standard components. Also part of that creating volumes, and then scaling it, which also involves creation of volumes, right? So that's the magic of providing dynamic provisioning in this environment. Okay, let's see, I had something on this. Yeah, so the last thing I wanted to show was how easy is it to get rid of it, right? So I've done so much, I've created so many components, right? Yeah.
Oh, can you also change the size of the first 2 storage that was already?
You mean the volume size?
Yeah.
So from a storage system point of view, I can, but the Kubernetes community has been working on the extend functionality. So basically, there is an API which is, I think, in alpha or beta right now, which you can say, I want to extend this volume, or PVC. I want to extend this claim to from 5 to 10. So then it will do that in the background. So you can do that, but it's not production. It's not productive yet. So that's a feature that is coming. So the last thing I wanted to show was how do you get rid of this. So that is also one single command: helm delete --purge, and what was the name? MyPSQL. It takes a little bit of time, but it is actually going to get rid of the stateful set, the services, the cluster role, every component that was created as part of it. It is going to get rid of it. But it will not get rid of the volumes. Your volumes need to be separately deleted because it's a stateful set. They are made in such a way that the data is not that easy to delete because it could be a database which you want to delete. So you have to delete that manually. So it takes its own time, but everything is done automatically in the background. So far good. Any questions?
Question down here.
Questions? All right. So it's kubectl get all. If I do, so you can see everything is gone. There's nothing remaining anymore. But I will show you that PVCs are still there. So the data is not gone. You have to delete it. All right. So I have a couple of more slides, which I just want to touch on. So many times when I'm giving talks or talking to people, they always ask, okay, if I give this possibility to dynamically create volumes, developers are going to go crazy and create like terabytes and terabytes of volumes. So there is, this is a question which I get all the time. So that's why I thought I will talk about it. So there is something called resource quotas in Kubernetes. And you can say, I want this particular project or namespace to have these many persistent volume claims or this much volume. You can give size and number both, and you can mix and match that as well. So a cluster administrator has to give quotas, like in a cloud environment, to the developer or a team of developers in which they can operate, and then they have to probably ask for request for more of them. So quotas are we are able to provide that. For example, you cannot do something like this in Docker Swarm, for example, or Docker Data Center. So this is pretty cool. And not only this, you can also set these quotas, of course, on CPU and memory. So it is complementary to that. So you give a developer or a team a workspace in which they have a set amount of CPUs, a set amount of memory, and a set amount of storage. Say gold storage, which is 100 gigs or something like that. Right? So you can set up all those things with quotas. So whatever I showed you, this is all applicable to Kubernetes. And there has been an initiative like CNI, which is Container Networking Interface. You must have heard of it, and it was also in the slides previously. Similarly, we are working on something called Container Storage Interface. So the effort is to actually create an interface or work in such a way that, like, you can use Flannel or Calico in Docker environment or in a Kubernetes environment. Similarly, when the CSI is out, you can use Docker Data Center or you can use Mesos. You still use the same plugins from storage vendors or storage systems or Azure or Amazon or something like that, right? So we are going to standardize it for all the different orchestration platforms. And there's already an alpha out, so if you want to know about it, there's an alpha out and there's a blog out as well, which came out this month, I think on the 18th. And there's also a spec on what they want to do. So this kind of dynamic provisioning with different storage plugins will happen in Docker Data Center or Mesos or Rancher or everything, and they are all working together to actually do this. And we are also working together with them as a community. So Netapp is very active in all the open source projects. So if you see on the right hand side, there is the netapp.io. This is dedicated to all the open source work that we do. So like OpenStack, we do lots of contributions to Cinder and Manila. Manila was actually a file share services project in OpenStack, which we founded. And we also do contributions, for example, in CSI, the container storage interface, and we are doing container management, storage management kind of work, because we kind of understand storage, and when it comes to deploying databases and things like that, we want to contribute to the community as well. So some resources. So if you are interested in this, you like Trident and you would like to know more about how dynamic provisioning works, we have a Slack channel. We have lots of our developer guys who are on the Slack channel. We have everything is open source, whatever you see on the right hand side, netapp.io. And yeah, you feel free to drop by on our Slack channel. Now I'm open for questions. That's all I had to share. Yeah.
Is it possible to take snapshots of volume using Trident?
So with Trident, you can say, I want to use a snapshot policy. So on a storage system, you have an hourly policy or say a daily policy.
Yeah.
So the volumes will automatically be snapshotted. So that is something most of our users use, because the storage admins don't trust the developers and they always want to take snapshots. So you can set a default policy on every volume, say hourly or daily, and the snapshots will be deleted after a while or something like that. So that is possible, and the developer can also say, as part of a persistent volume claim, that I want this volume to be snapshotted daily or hourly, or defined policies can be set on the storage system, and then they can be consumed here.
Actually, we use Cinder. We can do snapshots of backup of
yes.
volumes.
Yeah, but for that there needs to be an implementation of that, right? So
I think for us, if you want to back up nodes, we need to go to Cinder and
right, exactly. But if in the Cinder provisioner there is a snapshot policy, but Cinder doesn't have snapshot policies, right? That's the problem there. In Cinder, you can do it on demand.
On demand, yes.
Yeah. So you can say, in the backend, I'm just setting such policies. But that is always helpful for the storage guys to actually set a default, so that there is always, sometimes they say, okay, we lost the data, but the storage guy says, oh, don't worry, I have the snapshot and I can help you out. So that happens actually a lot. And you can also set different, create cloning. So that is the cool feature that we just came out with. So for example, in this case, that is something I want to work next on. So when I have a storage system and I want to scale a Postgres database, maybe I can just use clones to scale it, right? So instead of, so say I have one database which is 300 gigs, right? Postgres database. And now I want to scale this database. So as soon as I create a new instance, the whole replication will happen from one node to other, right? But if I could actually create a clone on the storage side, and then say Postgres use this as the volume, then there is no replication, there's no CPU utilization required, there's no network required, and then you can just create clones and scale your database, which could actually prove very, very helpful. If you have like 1 gig, 2 gig test databases, you will not notice such things. But if you're actually running in production, you have huge databases and you want to scale them, these things come play a big role in such deployments. So if we could create a Helm chart which could automatically do that, that's the kind of thing I would like to see, because when it comes to storage, if I tell a developer that you can do these things on a storage system, he has no access to it, so it becomes difficult. But if you have integrations like these where dynamic provisioning can happen and quotas can be set, then you can actually leverage the goodness of the system, and the integration are actually creating the positive value, right? So the developer has nothing to do with the storage system. He's just saying, I want a gold storage of 10 gigs, which should have snapshots created so many times. That's it. Right? He has no access to a storage system. He doesn't want to think about it. Something like object storage. Right? All developers want object storage-like experience. And these integrations can actually kind of help you get that experience of object storage kind of experience. I just call an API, right? And things happen for me.
Is there any drivers for Cinder?
Yes, there is a Kubernetes provisioner for Cinder as well.
Or we can use it for Cinder also?
Yes. I tried to use it, but I could not get it working, but there is one. As in, there's some work to do, but there is one available.
Okay.
So I showed actually of all the ones that are available. These are the ones. Already. Yeah.
With a StatefulSets and Helm charts like this, how would you? Is there a way to upgrade the deployed application?
Yes. So Helm charts are also versioned. So you can say I want to upgrade my Helm chart or this application with this Helm chart. So you can do that. So it also comes with the upgrade mechanism. But I haven't tried it yet. That's a good question. Maybe I should try it. Maybe that could be the third, one command thing that I upgrade.
Sort of to follow up on that, maybe I guess if you would have to shut down the master if you upgrade, so it would not be.
He's talking about upgrading the Postgres.
Oh, upgrade. But if you upgrade the replica set number 0, right, you would probably not be able to write into the Postgres since it's the master where all the writes are going through. Right? So
probably there are some challenges around that.
Yes,
yeah.
you would not.
But I haven't really explored that. My job is to showcase how cool it is to dynamic provision. But those problems still remain, as in many people have tried. Yeah.
So, you done?
Oh, I'm done.
You go ahead and then.
Okay, so this storage class defined the goals that you are going to Trident specific only, or how does it work?
No, it has nothing to do with Trident. So I can actually show you kubectl get. So I have defined different ones. This is basically in a storage class you define which provisioner you want to use, right? And in Netapp provisioner I can say backend type should be ONTAP NAS. This is my implementation, right? But for example, maybe in Amazon you have a storage type gold, which is Amazon provisioner plus SSD, for example. So that would be gold for you. So a gold will be created, and things like that. So you can have different kind of. This is just a definition, right? So in this, it is clearly saying that use this provisioner. So use the Netapp provisioner, and Netapp provisioner should use this one. So if I show you gold, for example, from SolidFire, you will see that it says, I want this storage system with gold. And gold is actually already defined with IOPS in the backend by the storage API or the cluster API. So you can define these, and like for OpenStack also, there are the different provisioners, so you just define that provisioner. Yeah. That's it. Any other questions? That's it. Thank you very much.